They're gonna work.
Good question.
Good question. All right, we're gonna talk about quickly different rainfall methods in GSSHA. And this really just kind of show you what is available. If you were going to use them, you would need to go to the wiki or contact us and get some help with it. But we're just going to blast through it and show you what there is. So precipitation types, there's uniform rainfall, which I think we've been using, spatially uniform, temporally varying, like the hydrographs. I think we may have used those already. I know Chris showed them. And then spatially and temporally varying rainfall, which is really what you use to do a study or project. With the uniform rainfall, I think we've been through that. You've done it, so you know how it works. We'll skip that one. Spatially uniform, temporally varying rainfall. So that's the single gauge with the XY time series. You specify that time series, and typically you go through and pick one, like a Pearson type 2 or whatever. And so then those are standard storm events that a lot of times they're requirements of a project to run. You must run the 50-year, 24-hour storm event or whatever. And that's useful for that. So the spatially and temporally varying precipitation, you have to build these things external to the WMS. Specify gauge locations and rain rate with a non-uniform time spacing. And then there's a bunch of different formats for entering rainfall, because you can get your rainfall in all kinds of formats. So we try to accommodate as much of that as possible without a tremendous amount of work. And so the gauge data input file, it's a card-based input file where you specify the event, how many gauges you have, the coordinates of those gauges, and rainfall source card. There's different ways to put it in. One thing I mentioned here is that I know that Chris said, when you're setting your model up, you could go in a state plane projection or some of these other projections. I would say always set your model up in UTM, because when you get these coordinates are going to be UTM coordinates. And so if you get product from forecast from WRF or something, it's going to be in UTM. So I would always set the model up in UTM, and then pick the standard datums like the NED 83 and the NAVD 84, especially if you're a core person, because those are our standards. So I would always pick those. That has nothing to do with rainfall, but it kind of does. So there's an example of what one of these looks like. Tells you the name of the event, which can be anything you like, the number of points in your file, the number of gauges, and then those coordinates like we talked about, and then the rainfall specified for each of the gauges. In this particular example, it's a radar. Rainfall file conversion. I don't know what that was about.
It's utilities we have on this.
Oh, was that the wiki?
Yeah, it's just.
Oh, okay. So yeah, so on the wiki, well, I can't see that. Can you see that? Aaron showed you there was their utilities. There's a spreadsheet and there's Python scripts to build these files for you. And so you don't have to build these files from scratch. You can either use the spreadsheet, which we used for 20 years, and then until some Python programmers came along and said, oh, we can do this a lot better. And so they built scripts to do the stuff with Python. So whichever you prefer, if you're a spreadsheet person or a Python person, you have utilities. Because when you get hundreds of gauges and years of simulation, you need help, basically. So guide for rain gauge selection. So gauge is sensitive to rainfall input. So if you put poor input data in, you'll get poor model results out. So for the best results, you want to get multiple gauges located within inside the watershed. And for convective storms, like a thunderstorm, so research indicates you get a very poor correlation between gauges more than 50 kilometers apart. So that's kind of That's kind of something to keep in the back of your mind. So always include nearby gauges outside of the watershed, because those are going to help give you a better estimation of the rainfall inside the watershed. Don't put stuff that's 100 miles away or something. It's not going to help. It's going to hurt. Always input the finest temporal resolution of rainfall possible. Don't ever take 15-minute rain gauge data and put it up to a day. You lose all the information. So, if you have gauges, all the gauges, the time step can vary between like one step to the next, and it can be like 7 minutes and 15 minutes and an hour or whatever. But so a lot of times, especially if you have a whole bunch of gauges, some gauges are 15 minutes, some gauges are hours, some gauges are day. Always make everything 15 minutes or whatever the finest is, and instead of going the other way. Oh, well, I have a daily gauge, so I'm gonna make everything daily. Do it the other way around. So keep as much of the information as humanly possible. You're gonna get a much better model. Spatial distribution, you can either specify decent polygons or inverse distance weighted inverse distance squared weighted. That's hard to say. So these and polygons can be used to represent any gridded product that you might get, like a radar or a weather forecast is going to come on a grid. So you can, if polygon would represent that gridded product appropriately. So just here's a picture of rain gauges in a watershed with Thiessen polygons. Here's a picture of a watershed with a radar grid laid over the top of it, with again Thiessen polygons. So you can see the Thiessen polygons. If you pick Thiessen polygons with a radar grid, you'll get the radar grid at the center of the Thiessen polygon, which is what you want. It's just snapfall rainfall intensity. One of the things you can do is you can output your rainfall intensity maps, and you can get an idea where the rain is falling hard and when. And then sometimes it can help you figure out problems with your model, because you think you should have got more runoff or less runoff, and then if you can look at these distributions, well, you have a really high intensity in this snapshot, but it's only in one quarter of one cell, and so it's like, wow, I had a really high rainfall rate. Why didn't I get any runoff? Well, it's very poor. It's very little, minimal coverage. So visualizing those can be nice. Here's the same watershed. In this watershed, there were 3 gauges outside of the watershed, and that's a inverse distance weighted distribution. It's really poor. It was really poor distribution, and then a radar was a much better solution for this particular watershed than the gauge network, which was non-existent, I guess is almost the word used. Plant interception. So you can specify plant interception. Don't always use plant interception, but especially if you have a forested area, plant interception can be a pretty big chunk, and you can put a retention depth in, and they in a way they kind of are similar, but the thing about plant interception is it takes the water out of the base, and retention depth holds it, and it'll infiltrate, and it'll raise the soil moisture, which we've already seen will decrease the infiltration in the next rainfall. So the plant interception model's in there. There's a 2-parameter. You specify the initial volume of rainfall, how much rainfall has to fall before it starts to run off. And you can think about if you've ever been in rain and you run under a big tree, and for like 20 minutes it's completely dry, and then the damn thing starts dripping on you. Well, it has to get that initial volume, and then it'll retain a fraction of the rainfall after that. And so somewhere around 15%, in a jungle it can be like 30%, so it can be substantial. So the inputs for interception, of course, we use our index map and our mapping table, and that's derived from a vegetation coverage. Could be land use if that's what you have. A vegetation map would be better. So then you'll have the table, and the table will of course have the 2 things we just talked about. Applications. So we use uniform rainfall really to set models up and get them working. Real watersheds are simulated with multiple gauges and temporarily varying rainfall. Radar rainfall estimates are useful when the good gauge data are not available. Currently exploring the use of satellite data for remote regions. It's terrible. Basically, it's either good in time and bad in space, or bad in space and good in time. Whatever. It needs work. I'm not going to talk about that. Multiple gauges are created, but each gauge just have the same distribution of rainfall, and a rainfall gauge coverage is created in your WMS. So even though you build these things outside of WMS, you can visualize them in WMS. So you can look at all your different rainfall events. I'll warn you that if you have a rainfall gauge that has 500 events in it, you need to like turn off that visualization of that coverage before you bring it in, or it'll take 4 hours for it to come in WMS. So if you get stuck in your that can be it. So using a hyetograph, that's really for looking at design storms. And I think you've done it, so we'll talk about it. Using gauges, so the gauges are created in your rain gauge coverage. So WMS automatically generate Thiessen polygons as the gauges are created. So it shows you, how the rainfall is distributed. And that's what it would look like in WMS. Using gauges, so the temporal distribution of the rainfall, the rate or depth in each gauge is defined by double-clicking on each gauge under rainfall coverage. The depth should be incremental millimeters. So your gauge is metric. Everything's metric. So rainfall is millimeters. Make sure you use millimeters, not centimeters, meters. Causes problems. So sometimes you'll get, when you get rainfall, it comes in all kinds of crazy units. It might be inches, it might be millimeters, it might be centimeters. It can really be a mess to sort through rainfall data. Just keep it in mind. So that's just a visualization of rainfall. So using gauges. So once all the gauges are defined, you go back to the gauge precipitation, rain gauge coverage, get the gauge information. So this is just how we do it in WMS. So using NexRad. So we can use NexRad radar data. And it's just a gridded product. So, that's just a visualization of some NexRad radar from, I guess, the New Orleans radar. So what's NexRad is developed by the National Weather Service. Imagine that. It stands for Next Generation Radar, in case you've always wondered. It's the WSR-88D weather radar. So NexRad senses the rainfall by transmitting a radio signal and measuring the reflection from the falling drops. The data are available in 2 kilometers by 2 kilometer grids. So NexRad doesn't actually measure rainfall. It kind of measures potential rainfall. So you got to kind of keep that in mind, because sometimes the potential rainfall doesn't turn out to be the rainfall. And NexRad shoots out on an angle. So the further away you are, the higher it's shooting up into the cloud. And at some point, it's useless. And so you got to think about that. Am I so far away from the radar that I'm not really measuring rainfall? It's hitting the ground anymore. And so you get NexRad everywhere. I think when we built this slide, NexRad was brand new. We were the only people in the world actually collecting it and storing it. You can imagine such a thing. We were the first people using it for anything, including hydrology. So like I just said, the best thing about the radar data is you get a nice distribution. Sometimes, depending on where you are, your volumes aren't great, and if you have a decent gauge network, you can correct the bias and the amounts with the rain gauge, but you have a superior distribution. So you will kind of want your rainfall volumes to match your gauges, but you might want to use the next rad anyway and adjust it because it gives you that superior distribution of rainfall. So processing, I don't want to talk about. We're not going to do it. It's all in the tutorials and the wiki and the, you can figure it out. We have phones, you can use them to call us. Other methods of rainfall, like I said, satellite and remote sense rainfall data, which as of now are still not good. There's other sources of rainfall. There's a PRISM data set. This is the old presentation. I think I changed this presentation and didn't get into the, didn't get in. You can also get precipitation estimates from River Forecast Center, the CNRFC. You can get, there's a lot of forecasted products available, a lot of models from the US and Europe as well, and you can get the net CDFs of those. You can get those data, and they come in net CDFs, and any net CDF data can be processed with a tool we have called GSSHA, and they can be used as inputs into GSSHA. This shows you one forecast from scripts. They use a model called West WRF, which is a special implementation of the WRF model for the Western United States. And that's all I have.